Hello, everyone. Today we'll be going over the XL-18 flamethrower phase 3 part of the project. The group members are Taylor B., Ethan Myers, and myself, John Scotto. The contents we're going to be going over: introduction and objectives of project for the proposal, team member introduction, system design overview and performance standards, safety and compliance, mechanisms of heat transfer, overview of heat transfer mode across system, mathematical modeling of the system, analysis of original design heat transfer modes, discussion, simulation confidence, improvement suggestions, numerical analysis of improvements, and the conclusion and references. The XL-18 flamethrower exemplifies cutting-edge engineering principles in heat transfer, demonstrating interplay of conduction, convection, and radiation. While originally designed as a weapon, modern flamethrowers have diversified applications in agriculture, firefighting, pest control, and emergency operations. The flamethrower's ability to deliver concentrated, rapid heat makes it a valuable tool in specific situations where conventional methods are impractical.
Moving on to the system design overview and performance standards, the XL18 flamethrower operates using a higher pressure CO2 system to eject flammable fuel and maintain consistent combustion. Included here is a table showing some design specifications, such as the effective range, fuel capacity, and CO2 capacity, tank capacity. Some of the key specs is the effective range of 110 feet. The system is compatible with multiple different types of fuel, such as diesel, gasoline, or napalm, or a mix of that. And then also that there's a maximum continuous fire of only 6 to 7 seconds, given that we have a fuel rate of roughly half a gallon a second, and that we only have a fuel capacity of about 3 gallons. Moving on to the safety and compliance. The components are all going to have to meet some type of criteria to make sure they're safe. An example of these criteria is the tanks, the fuel holding tanks. They're subject to adhere to UL142 and UL2085. These specifications set like standards for the materials, the compositions, essentially the metallic or the mechanical principles to make sure that they're able to uphold and stay structurally sound over time and endure the abuse. There's a few redundant safety features incorporated in the system. One of them is the fact that we're using CO2. Since CO2 is kind of the pusher, you can kind of think of that we have in the system, we have 2 tanks. The CO2 pushes the gasoline or napalm or diesel, whatever mix you have, out. And since CO2 is expanding and it's filling in that tank, there's no chance for backfire because there's no chance for combustion to happen if there's no oxygen. If CO2 is in the place, there's no combustion can't happen. In addition to this, because it is a human mounted system and it's made to be carried by a person, we're limited by what a typical person is going to be able to carry and realistically what they would want to use. So the system already weighs 53 pounds dry. Gasoline, which is the lightest of the fuels that we mentioned, weighs roughly 6 pounds a gallon. So with just over a 3-gallon capacity, that's about a 70-pound system, when it's all filled and all said and done. So you're limited just by the sheer fact of how much you carry, which is a bit of a safety benefit anyways. Although not related to the heat transfer design, which we'll talk about later, there's still other places for improvement. One of these could be a safety shut-off mechanism, essentially to make sure that if there's an emergency where the gas is flowing uncontrollably, you're able to shut it off and prevent any unsafe spilling of gas or any gas being expelled. For the mechanisms heat transfer, the system uses all three primary modes of heat transfer: conduction, convection, and radiation. Conduction occurs in two different spots of the system, the first being at the fuel tank, the fuel interface, and the second being condensation occurring. Uh, for convection, convection dominates this whole system. Essentially, convection, forced convection, really, because we have compressed CO2, it's what drives the flame out of the system or out of the wand or nozzle. And then radiation. Radiation allows heat transfer to occur, and it allows heat to transfer over distances and making the system effective even without direct flame contact. And we can see this picture here shows the four main methods of heat transfer. So it could show the fuel tank, or I'm sorry, the three main modes of heat transfer, but it shows where they happen in the four different places. Now, modeling the system, we can rely on the three primary heat transfer rates, which are given through our textbook. For conduction, that relies on Fourier's law, which states that it's the thermal conductivity times the difference in temperatures over the distance. Similarly, for Newton's or for convection, we can use Newton's law of cooling, which states that it's H, which is a coefficient of convection heat transfer multiplied by the difference of the temperatures. For radiation, we use the Stefan-Boltzmann law, which states in a similar concept to the convection, we have an emissivity, a Stefan-Boltzmann constant, and then we have the difference of the two temperatures. However, both of those are being raised to the fourth power. Moving on to the computational results, we have the four different stages of the system and their values, respectively.
So we took an energy in, energy out approach. We knew how warm the outside was. We assumed there was no wind. We assumed that the flamethrower had been sitting outside for a while, and thus the fuel inside and the walls of the container and the nozzle and everything was the same temperature, which was the outside temperature. We knew how warm it was outside. We knew how warm it was inside the flamethrower. And we also knew how hot the torch got, the pilot torch that starts the flamethrower. And we also knew the potential chemical energy of the fuel, and we also knew the potential energy of the CO2 canister. And just a little reminder, the way the flamethrower works is you got a CO2 canister right here. I'm trying to get this in the view right here. And then that pushes gas, it goes up, and then it goes into a bigger tank full of the fuel, and it pushes the fuel out like this into the nozzle. And in the nozzle there is a little, right before the nozzle there's a little pilot torch, goes over it, ignites, and then mixes with air, and out comes flame. So limiting our calculations to the content of this class, we only use the three main types of heat transfer, which is conduction, convection, and radiation. So a little reminder, conduction is surface to surface heat transfer. Radiation is just energy across space, like radio waves and things. And then last one is convection, which is a fluid against a surface. And then for our original analysis, we had a 4-point approach. So first up, we looked at the conduction between the fuel tank and the fuel. We knew the temperature outside, and we knew where the fuel was. And then we looked at the conduction between the flame and the fuel, the pilot flame and the fuel. That was conduction based. And then we did a convection based one between the ignition and the torch flame. So imagine the fuel swirling around in there in the atomization chamber of the nozzle. And then we finally did a radiation based one, just assuming that the flame would fly forever and it would lose all of its energy via radiation. So we saw what that would be. Again, very energy in, energy out approach. Okay, so we did all of our more advanced calculations in ANSYS Fluent. Now, ANSYS Fluent is very expensive if you get the full version. The student version is very capable, however, there are a few things that it does not do, and those just happen to be the things that a flamethrower does. So we got ignition. Very difficult to model, very computerly complex, lots of resources that I and our team does not have the availability of, nor the ANSYS model, the ANSYS Fluent version to use. So we took a very dumbed down approach. Made a lot of assumptions. Firstly, we did a 2D model instead of a 3D one. There'll be a picture of that in the next slide. That really simplified calculations. However, we also lost out on the potential for the nozzle to induce any like 3D gyration to create more of an atomization effect. So imagine like rotating the fuel as it's going through to get some more velocity and therefore more air in there. We also assumed that the nozzle didn't do anything else like change the total energy by like sucking air in, which it probably did by a Venturi effect. We also assumed that the CO2 canister wasn't losing pressure while it was going. So CO2 canister, as it loses, as it's pushing out the fuel, it will lose some of its pressure while it's doing that. The CO2 canister, according to the manufacturer, will last a few full tanks, but it still is a noticeable amount. And because we couldn't find data on how many tanks, full tanks of fuel the CO2 canister will last. It was a 20-ounce CO2 canister, FYI. We just skipped over it and assumed it was just a constant pressure. The results of this being the flamethrower made it its full 110 and sometimes a little bit more feet that it was advertised. Also a little confirmation of the data of our model. However, there were some shortfalls in our model. The main one being it appears because of our limited computing resources and limited modeling, the flame reached its full chemical potential energy rather than what actual flamethrowers from like World War II or Korea reach, which is 1,000 Kelvin difference. And also all three of the fuels behaved very similarly. In some points their temperature gradients were within degrees of each other, singular degrees. So we believe that our ANSYS fluid model had some serious issues with ignition and combustion specifically. Moving on. So from a purely heat transfer standpoint, there are a few improvements we could make to the flamethrower. Now, obviously, the point of a flamethrower is to transfer energy over a distance, but from the heat transfer perspective, we could chase the higher chemical temperature and therefore transfer more energy to the target faster, just assuming that there was no range intended travel. So we removed the trade-off and we just assumed maybe the user is wearing a very protective suit and there's a big ice wall in front of them and he just wants to get in there. So how can we do this? How can we get the flame hotter? Well, we could improve the atomization. So in the nozzle, rather than focusing on maybe like a swirl effect or only igniting like a certain amount of the flame but consistently so it doesn't like go out, we could like a spray paint or just automotive paint system. We could improve the atomization, therefore separating all the little fuel molecules, and then mix in air the best we can, so that all of the fuel has all the air it could want, and well, has the proper amount of air it could want. So the stoichiometric ratio, and then burns closer to its theoretical hottest temperature. Now, that would increase the flame temperature, but another interesting thing to do is just increase the flame temperature directly. So maybe in an oddball situation, like you're in a factory or some other controlled environment, you could use electricity to heat up the flame also, and get it a lot closer to its ignition point before it actually needs to be ignited, which would make it a little bit more consistent. And you would be transferring, although a small amount of energy as compared to the chemical energy contained, it would be a noticeable amount, and it would make the flame a little bit more consistent, especially in varying conditions, to have closer to ignition fuel That will, of course, require more safety involved, safety procedures in the flamethrower to make sure it does not pre-ignite. Just keeping the air out mostly, but there's other issues of heat soak with increasing the flame, preheating the fuel without injuring the user. And finally, as kind of like an address to increasing the flame temperature by a preheating, we could coat the whole, we could use thermal coatings on the whole thing. So think of like a ceramic coating or some sort of like engine block coating, like just to make it a little bit harder for that heat to transfer, even though it will eventually transfer with a reasonable amount of coating that doesn't weigh so much that the user can't even put the backpack for the flamethrower on. In the short term, with a portable flamethrower, it will make a difference if the user doesn't have to worry about accidentally touching the nozzle or something and burning his hand pretty badly by conduction, if there is a little insulating layer on there that will slow down that heat soak. So after this was all done, we took a little numerical analysis of some of our potential improvements. The one we focused on, the one we found the most interesting and achievable, was the preheated fuel idea. So let's say you increased the fuel temperature 50 Celsius or 50 Kelvin, which takes quite a lot of energy with a big tank of fuel. And what would that do? What would that do for it? Well, theoretically, in my head, when we were putting this together, I thought, well, we'll get 50 degrees hotter. But in actuality, it was more like 7, 8, or 1 or 2. It didn't make a huge difference for the amount of energy that went into it in the preheated fuel. And that's just due to the nature of combustion. That energy is not going to change the chemical, like how the fuel burns with air while it's in motion, and how fast it can burn, and how it's competing with like the pressure of the pressure gaps caused by its neighboring fuel igniting. But it didn't make a difference. It didn't just, in our math, it didn't just get ruled out. So this leads to some possible further numerical analysis. Firstly, we would like to try Fluent with a much more powerful computer and possibly a better version. Using our model, it would be as simple as clicking a few more buttons and it would run a bunch more equations. That would require a lot more computing power, especially if we go into the 3D realm. My simulations took about 30 seconds to a minute to run for each of the fuels. There was a little bit of fidgeting in there between the trials to make sure that it accounted for the different fuels. And we achieved stability, which was the endpoint of the simulation, was when the changes in variables became marginal. So we would like to do that. The easy thing we could do in ANSYS, though, would be modeling the CO2 canister. That would be very interesting to see what the different pressure pushing out the fuel decreasing would do. That would be as simple as a little bit of differential math. Now, outside of ANSYS Fluent, we could try some more exotic preheating methods. So what if the gas or the fuel came out in a gaseous state instead of a liquid one? Or what if it came out in a plasma state? How would that affect it? Or would it even really be a chemical reaction? Would it combust at all? Would it need a super hot preheater? Things like that we just don't really understand at this point in our studies, but we find interesting. Finally, it wouldn't be too difficult to put the thermal coatings on the flamethrower in our model and see what that would do. Like, how long would it take for the heat to soak through the steel pipe that makes the little squirter thing, like the little, I don't want to say gun, but the applicator. If we put some sort of ceramic coating on there, how long will it take before it burns someone?
In conclusion, the XL-18 remains highly effective for applications like movie, special effects, and agricultural/forestry controlled burns. while also showing potential for further optimization. The XL-18 flamethrower showcases the use of conduction, convection, and radiation in its heat transfer processes. Numerical modeling, MATLAB, and ANSYS was used to analyze the system across 4 key stages of operation. Proposed design improvements such as fuel preheating demonstrated measurable enhancements, increasing the maximum burn temperature by over 7 Kelvin. Thanks again for everyone for watching our presentation. We really appreciate it, and have a great day.